Says 2.6a related rates. Related rates are rates that are related. So we have these functions. We have a y equals x squared plus 3. And I need to find dy dt. And then I'm given a couple things. I'm given that x equals 1. And I'm given that dx dt is equal to 2 when x is equal to 1. Right. Well, how do I get to dy dt? What do I actually need to differentiate with respect to do it with a dy dt popping out? I need to differentiate this function with respect to what? T. So you don't have to write this ddt part, but this is really what we're doing. We're deriving this function. Actually, it doesn't have to be a function. It could be a relation. This relation with respect to t. So what is the derivative of y with respect to t? dy dt is equal to, what's the derivative of x squared with respect to t? 2x, and then a dx dt pops out. And then the derivative of 3 is still what? 0. So we don't have to put anything. And so from there, all we do is we just substitute in what we know. And so we're solving for dy dt when x is equal to 1 and dx dt is equal to 2. So we're just going to substitute in our 1 for x and our 2 for dx dt, and we end up getting dy dt is equal to 4. So a lot of related rate problems are knowing how to read. And that's our struggle a lot of the times in mathematics is we don't really know how to read very well. And so that's what we're going to work on right here. So it says the velocity of a car is traveling for 1 hour is 50 miles per hour. And so what we need to do is we need to talk about like a time and we need to talk about a distance. And so if our distance is related by x, our rate is miles per hour. So that's our velocity. And so how could I notate giving a velocity in terms of x and t? A dx dt, because I'm taking a derivative of position over time. And so that's a dx dt is equal to 50 when our time is equal to 1 hour. All right, let's look at the next one. So we got water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. And so if I were to fill a pool, what do we actually have? Is it volume? Is it area? Is it just a constant? We have volume in a pool. And so if I have volume in a pool, it is at a rate of 10 cubic meters per hour. So what that is a related rate. And so it's dv dt is equal to this 10 cubic meters per hour. All right.
Okay. A pebble is dropped a hairbrush is dropped into a calm pond, causing ripples to form of concentric circles as shown in figure 2.34. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the
Disturbed water. Changing. All right, beautiful. All right, so it says the radius is increasing at a rate. So the radius is increasing at a rate. So what does that actually say? That says dr dt. It's not the radius, but it's the radius changing at a rate. And so dr dt is equal to 1 because it says it's of 1 foot per second. And then it says when the radius is what? 4 feet. So is that a rate? No, that says my radius is 4 feet. And then it says at what rate is the area changing? So this is actually finding the area changing. So what rate is it changing? So is that a related rate or is that just an area? That's a related rate. And so what we're trying to solve for is dA dt. We're trying to figure out what my area is changing with respect to time. And so all of these are circles. And so we need an equation of an area circle thing. And so what is the area of a circle? Pi r squared. Okay, and they won't give that to you. You will have to know that area is equal to pi r squared. All right, and so now what do I need to get to? I need to get to dr dt's and dA dt's. So how do I get from A to dA dt? I take a derivative with respect to what? t. So let's do it. So the derivative of a is dA dt, which is equal to pi r squared. Now, pi is just a constant multiple. It's a number, all right? And then our variable is r, and so what's the derivative of r squared? 2r. So now I end up having 2 pi r, but what pops out? Because I know implicitly. 2 dr dt, all right? Now, without making a huge deal of it right now, if I go from pi r squared to 2 pi r squared is an area, right? What's 2 pi r represented as? It's circumference. So I went from 2 dimensions to 1. All right. So without making too big of a deal, that's not the lesson. Let's keep moving. All right, and so now we have dA dt and it's equal to 2 pi r dr dt. And so now we're just going to substitute in everything we know. And so I'm solving for dA dt. So dA dt is equal to 2 pi, and my r is 4, and my dr dt is 1. And so dA dt is equal to 8 pi. Here we go.
Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet.
All right, fantastic. So air is being pumped into a spherical balloon. So what is being done here? What's changing?
Air is getting pumped. Well, the volume.
Volume is changing. So what they told me is that dV dt is what? 4.5. I'm going to use 9/2 because fractions are easier to work with. All right, and then it asks, find the rate of change of the radius. So what's being asked to solve for? dr dt. That's what's being solved for. That's my question mark. And then it says when the radius is 2. So r is equal to 2. All right, now they will probably give you an equation. We don't. All right, so volume. So we're going to go back to geometry. What's the volume of a sphere? 4/3 pi r cubed. Very good. All right. And so they will actually give you that one. I'll give it to you as well. And so now we're going to take a what? A derivative. So dV dt is equal to, what's the derivative of 4/3 pi r cubed? So 4/3 pi is just a constant multiple. So what's the derivative of r cubed?
3r squared.
So we bring that down. So the 3 plays with the 4/3 to become what? So we got 4, and then pi, and then r squared dr dt. Now, I'm not going to talk about it too much, but I want to point it out. This is volume. Does anybody know what 4 pi r squared is?
It is.
It's the surface area of a sphere.
Oh my gosh.
So it went from what? 3 dimensions to
2 dimensions.
2 dimensions. I wonder if that was just random. All right, and so now we're just going to substitute in what we know. So what's my dV dt? 9/2. So now I'm going to just substitute in 9/2. And then I have a 4 pi. And what's my r? 2. So now I have a 2 squared dr dt. All right, so now we just do a little bit of math. 2 squared is 4. 4 times 4 is 16. So I got 16 pi over here. What do I want to do with it?
Divide it.
I want to divide it. And so now my dr dt would equal 9 over 32 pi. All right.
An airplane is flying on a flight path that will take it directly over a radar tracking station. As shown in figure 2.36, if s is decreasing at a rate of 400 miles per hour when s equals 10 miles, what is the speed of the plane?
All right, fantastic. So s is decreasing at a rate of 400 miles per hour. So what does that actually give us?
Negative.
ds dt. That's what it gives us, which is equal to what? Not 400, but negative 400, because it's decreasing at this rate. And then it says when s is equal to 10. All right. Now, it gave us a lovely picture right here. And so what kind of triangle did it make?
A right triangle.
A right triangle. So what do we need to do? It is a 3, 4, 5 triangle. You want to do that right now? Let's do it right now since it was brought up. All right. It is 3, 4, 5 day. You're right.
It's only natural.
All right. So the listeners, it is September 16th of 25. All right. So anyway, so 8 is what? Oh, sorry. X is
X is squared.
If this is 10, 6 miles above, how far is x? X is 8. All right, cool. So we need to find the speed of the plane, though. All right, and so what we need to do is we need to find its horizontal movement. And so what is being solved for our horizontal movement? It's not x, that's a distance. So what do we actually need to solve for? The derivative, which is notated as what? dx dt. That's what we're solving for. All right, because that's our rate. All right, and so what kind of triangle was it solved for again? It's a right triangle. What do we use for right triangles? We use Pythagoras. So we have x squared plus y squared is equal to, in this case, s squared. I'm usually going to use z, but this one gave us s to use, so we have to use it. And so now what do we need to take? Derivatives with respect to time. And so now let's take derivatives with respect to time. So what's the derivative of x squared? 2x dx dt. Beautiful. And then plus 2y dy dt. Beautiful. Is equal to 2s ds dt. And now we're just going to substitute in everything we know. However, it took me a couple of years to figure out, we can just cross out all these 2's and it'll be just fine. All right, so you don't have to multiply by 2's. It's less work for you. All right, and so what's x?
X is 8.
8. All right, we used that by our Pythag. It was just a Pythagorean triple. And so dx dt, do we know it? No, that's what we're solving for. And then plus my y happens to be 6. Does anybody know what dy dt is? It's 0. It's 0 because our plane is flying horizontally over the earth. All right, and so if it were negative, which way would it be going? Down. If it were positive, the plane would be moving up. All right, but this case it was 0. Is equal to, my s is what? 10. And ds dt is what? Negative 400. And so now we just have to do a little bit of math. So 10 times negative 400 is negative 4,000. We divide that by 8. So we get dx dt is equal to, not 500, but negative 500. Now, that's not my answer, though, Lane, which is, I think you were on the right track. Why is dx dt negative? Because x is actually getting smaller. All right. However, it asks for the speed, and speed is what?
Absolute value.
Absolute value velocity. So negative 500 is correct on dx dt, but our answer here, the speed is 500 miles per hour. All right, you have a few problems, maybe 6 or 7 problems there.